Alright, so here we go. We're going to do a quick little review here. So again, what causes an earthquake? Well, essentially it's deformation in the rock, and that rock's going to hold on until it can't let go anymore. Okay, so it's going to deform, then we're going to have a split along the fault, and then they're going to reline up. Okay, and all that energy that was put into this deformation of the rock is going to be released in the earthquake. Okay, we had two different major terms that we talked about. We talked about a focus and an epicenter. So a focus is the point underground at which those rocks finally gave way, and the epicenter is directly above that at the surface. Note the fault line that we see at the surface may not be exactly on the epicenter because of this, because most faults are actually at kind of an angle. Earthquakes release three different types of waves. We've got P waves, S waves, and then surface waves. Okay, and they come in that order. So P waves, these are primary waves. These are waves of compression and expansion. So we call these actually longitudinal waves. And these can travel through solids, liquids, and gases, and they are the fastest wave. Next we have secondary waves. Okay, and they travel in this manner, so like a transverse wave. Okay, they can only travel through solids, and they are slower than P waves. So we take this difference in the amount of time that it takes for them to reach an area in order to determine how far away that particular seismograph is from the earthquake itself. Surface waves, so these guys can either go in kind of this rolling motion or kind of in a back and forth motion. Either way, they don't travel very far away from the epicenter itself, but they are the ones that cause kind of the most damage. Okay, so seismograph or seismometer is essentially just a roll of paper that continues to go in a box that's placed on bedrock, with kind of a pen hanging with a pendulum. So the idea is that that pen should stay kind of still as the box kind of moves around, and that then records the shaking of the earth. Most earthquakes are located around the Pacific Ocean in what's called the Pacific Ring of Fire, along with plate boundaries. So that's the other place that we see a lot of them. In Canada and the United States, most of our earthquakes are on the west coast, with the United States getting significantly stronger earthquakes than we do here in Canada. Even scarier than an earthquake itself can be a tsunami, which is like one of the things that can cause tsunamis is an earthquake under the ocean, where we have a significant deformation of the bed. So whether that be a drop or an uplift, and that displacement of water has to go somewhere. When you are in the middle of the ocean, you don't really feel them much at all. You know, you may get like a little rise and a little fall, but they're traveling at great speeds, like 800 kilometers per hour, and yeah, we are only getting that 1 meter rise and fall in comparison to once it hits shore, where it can be several you know, tens of meters tall, and it's traveling much slower. So it's literally like what looks like a wall of water. And that's really what the only deaths in Canada, thanks to earthquakes, have been from, was a tsunami itself. We have two main different types of damage that can occur. One would be like liquefaction of the ground due to an earthquake, and we kind of had a video on that. We also have landslides that can be significantly dangerous. So we kind of obviously don't want to be building things in zones that get a lot of earthquakes. So we talked about behavior of waves. So we know that P waves get to a particular place before S waves do, because P waves travel faster than S waves, and that difference in time would allow us to determine how far away from a particular seismograph the epicenter was. We can use 3 seismographs in order to determine the exact location of of the epicenter of a particular earthquake. We then can use this information as well in order to calculate the strength of that earthquake on the Richter scale. So essentially what we do is we take the amplitude of the highest wave, and we take the time difference between the S and P wave, and we plot those on a chart, and then we draw a line between the two, and in the center is the Richter scale, and that will tell us exactly what the strength was, or the magnitude of it. So the important thing to know when it comes to the Richter scale is that this is a logarithmic scale. So we talked about how, you know, a 2 is 10 times stronger than a 1, a 3 is 100 times stronger than a 1, and a 4 is 1,000 times stronger than a 1. But at the same time, right, that 4 is only 10 times stronger than that 3. So it's this logarithmic scale, so every number just kind of represents a 10 times factor. So that's probably the most important thing to get out of Richter scales. We also know that the occurrence of earthquakes, as they get higher in strength, the occurrence is much, much less, with anything greater than an 8 being on average 1 a year. So in comparison to that, anything less than a 2, we get about 600,000 of those a year. So there's a huge difference in the odds of having a particular strength of earthquake. All right, with that was our lesson, and I hope you got a lot out of it.